Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Abdulaziz Al-Maari. Today I'm going to explain the last lab, which is about the Pelton turbine, and I'm going to go with the introduction, problem statement, and objective. Okay, in the introduction, the the Pelton wheel turbine are a form of hydro turbine, especially in M plus turbine that are extensively employed in hydroelectric projects. Actually, this built-in turbine, when the water is flowing swiftly and the turbine gets energy from it by slowing it down, making it an absolute turbine. The built-in turbine is a very simple machine to build a big circular disc to support by revolving shaft known as a rotator. The buckets are cup-shaped plates that are eventually placed over the circumference of the wheel and are installed in the circular disc. The buckets are normally set in pairs around the bottom. The following that nozzles are installed around the wheel to introduce water into the turbine. These nozzles fire water jet in the opposite direction as the turbine rotator, and the turbine spins due to the action of the water jets on the buckets. Lastly, the nozzle is set to completely open in this experiment. We go to the next slide, which about the problem statement. Our problem statement: the built-in wheel turbine generates electricity by utilizing water velocity and the flow rate of the water required to attain a specific level of efficiency to uncertain. In this experiment, a fully open nozzle is used. Thus, the water velocity remains constant. To attain appropriate efficiency, and the turbine rotational speed must be monitored. The objective of this study to investigate the operation of a Pelton wheel turbine and evaluate its efficiency, power output, flow rate of the water, and rotational speed using tachymeter. This is all from me, which about the introduction, problem statement, and objective part.
Assalamualaikum and good afternoon. My name is Mohammed SahrulFahmi with Senan, and I will present about the literature review of a Pelton turbine. Okay, a Pelton turbine or a Pelton wheel is a particular form of a hydro turbine, or more precisely, an impulse turbine that is widely employed in hydroelectric projects. Generally, these turbines are deployed on a site with a head more than 300 meters. The water in a Pelton turbine is traveling at a high rate of speed, and the turbine takes energy from the water by slowing it down and making this an impulsive turbine. Okay, this is the picture of example of a Pelton wind turbine. Okay, next I will talk about the design. Okay, when we design a Pelton turbine, we are utilized to generate electricity. A water reservoir is typically situated some distance above the Pelton turbine. So the reservoir is upward above the Pelton turbine. Okay, next the water then passes through the penstock to specialized nozzle that supply the turbine with pressurized water. Okay, the nozzle means that the fluid velocity is higher at the fluid out of the nozzle, so there is a push the turbine to move. Okay, to avoid a pressure variation, the penstock is equipped with a such tank that absorbs any abrupt change in water that could affect the pressure. Okay, lastly, unlike other type of turbine, the Pelton turbine is an impulse turbine. This simply implies that rather than moving in response to a reaction force, water generates an impulse on the turbine, causing it to spin. Okay, final part. I will talk about the turbine operation. Okay, the high velocity jets of water discharged from the turbine's nozzle. These nozzles are positioned in such a way that the water jet strike the bucket at splitter. The point in the bucket center where the water jet is split into two streams. Okay, we can show in the picture the high velocity nozzle will jet strike the bucket at the splitter. So the turbine bucket will move. Okay, the two distant streams that travel along the buckets in a curve and exit the opposite direction from which they are entered. This shift in the water momentum generates an impulse on the turbine blades, generating torque and spin in the turbine. The high-speed water jets are formed by forcing high-pressure water through nozzle at atmospheric pressure, for example, water falling from high hills. The greatest output of a Pelton turbine occurs when the blade generates the maximum impulse, which means that the water stream is deflected in the opposite direction and direction in which it impacts the bucket. Okay, that's all for my presentation part, which is a literature review, and I will pass a presentation to my friend. Okay, thank you.
Hello, my name is Tanjing Song. Now I will present the chapter 3, which is the methodology part of the third lab 5, which is the Pelton Wheel turbine. So before we proceed to the experiment, so there's a few safety precautions we need to obey. So which is, first we need to check all the connection of the water, and we are make sure that there is no leakage on the hydraulic branch. Besides that, we also need to make sure the spill valve is completely closed, and we also have to make sure that the storage tank is full of water. So the experiment is start with we turn on the hydraulic branch, and we are open the control valve while opening the spear controller, and which is turned into anti-clockwise until the branch valve is at this maximum, and the spear valve is fully opened. The hydraulic branch we use in this experiment is used to measure the initial flow reference, and the inlet and and the inlet pressure is recorded. So the water from the storage tanks will be pumped up and flow to the measuring tank level, and then we can measure the flow rate or the speed of the nozzle. So the tachometer in this experiment is used to measure the maximum rotational speed of the turbine, and tachometer is put against the clear glass and at the back of the turbine, and it is used to detect the reflective stiffness of the front. So the reading of the tachometer will be very slightly in the time. So, and the average rotational speed is estimated over the course of a few seconds. So the volumetric flow rate is determined by plugging out the drains at the bottom of the bench with the drain current. So the water line on the side of the bench will be observed. The timer will be started when the water reach from 0 liter, and it will stop when it is reached to 10 liter. So the volumetric flow rate will be obtained by dividing 10 liters. So the experiment will be repeated with reducing the RPM. That's all for me. Thank you.
Hello, hi, Assalamualaikum. My name is Ngarshin binti Salim. My matric number MA18204. So I will present about the result for this lab. First of all, this is the data one, turbine characteristic curve, and this one is the data two, which is power curve. Okay, from the data one, I get this graph, which is moment versus rotational speed. But for this graph, I actually change the data, which is from this table. As we can see, the starting from 600, which is the big value, and to the smaller value. So I just change and I put outside, which is from the smaller value to the big value to 601 and 13. Same goes to the moment of the shaft. I just change the value to relate with the rotational speed. So as you can see from here, I just change the rotational speed from the smaller to the bigger, and also the moment of the shaft, I just follow the value from the rotational speed. So I get this graph, which is the graph shows that the data was decreasing. What we can conclude from this graph, the higher the rotational speed, the smaller the moment of the turbine. And for the second graph, also I take from this graph from the first data. So I get the efficiency versus rotational speed, which is the rotational speed. Again, I change. So I just take from here the rotational speed, and also I change the efficiency value from the smaller one to the bigger one, as you can see at this outside. So I get this graph, which is at first the graph shows that increasing, but at the end of the graph, the graph was decreasing. So as what can I conclude is the higher the rotational speed, the smaller the efficiency. So this talk actually I calculate and I found that the value of the torque are same as the moment. So the torque I calculate by using the formula T is equal to pi and T over 60. So I will get this actually P out, and then I get this value. So for the third graph, this graph power out versus rotational speed, I take from the second data for the power curve, and I get this curve from the graph. So at first the graph shows that increasing, but at the end of the graph the data was decreasing. So the higher the rotational speed, the smaller the power output. So that's all from me. Thank you.
Assalamualaikum and good day. My name is Mohammed MA18261, and today I would like to walk you through to the tutorial discussion. So almost to the first question is how to calculate the torque pump. So we use the formula of P out is equals to 2 pi n T divided by 60. So the n represents the rotational speed based on the table 1, which is the highest, 613, which delivers the power output of 4.8. Just simply by substituting the formula, we will obtain the value of 0.05. So the second question, which is explain why the efficiency is low. So low head requires low energy and efficiency since the bucket speed is low and the kinetic energy required to the power wheel is low. Actually, it is closely related to the design of the Pelton wheel. The bucket shape is actually used to scoop the water by transferring the kinetic energy from the water, causing it to exit slowly. Thus, if the rotational speed of the turbine spins super fast, it will not catch the it will not transfer the kinetic energy from the water will be not transferred properly to the Pelton wheel turbine. At 470 rpm, the turbine generates highest power, which is at 3.2 watt. So the main function of the design is to feed the water source at low ratio of flow to pressure. So the main purpose of design is to ensure that the water exits
little speed and carry less kinetic energy as it was transferred to the scoop sheet or the bucket wheel at the Pelton turbine. So onwards to the next question, which is discuss about the graph. So there are three graphs based on the data given. Okay, so the first graph, it shows the steady declining of moment against the rotational speed from the first point until to the end of its point. So as for the second graph, it shows a steady incline followed by a downtrend. It reaches the top of efficiency when it rotates at 554 rotation per minute. After that, it slowly declines until it reaches to the bottom. So as for the last graph, which is the power versus rotational speed, it forms an uptrend from 180 rpm until it reaches the peak at 470 rpm. Then it starts to form a downtrend from 550 rpm until it transfers zero out. So also the last question for the discussion, which is explain about the graph. So this explanation was actually made based on the last graph, which is the graph 5.3. So according to CS 1990, the turbine should rotate half of the jet engine speed. Thus, it explains why at 470 rpm it delivers the highest power output, because if it rotates too slow, it will deliver less efficiency. Meanwhile, if it rotates too fast, the bucket scoop sheet will not catches the water jet that shoots the water at high velocity towards it. Thus, the efficiency will become zero. So, in a nutshell, we could summarize it that if the turbine spins too fast, it might not function properly, causing the spoon-shaped bucket to scoop less water, and as a result, it will deliver a lower power output and might deliver zero power output as well. This is because the energy transfer from the water to the spoon-shaped bucket was not transferred properly, thus the water exits the stream at a high velocity